This is Dr. Wood with the Citadel Civil Engineering Department, here to talk about CIVL 202 Statics, specifically Learning Objective 3.4.1, discussing frames and machines. Just as a reminder, statics is an incredibly important course because you're going to continue to use it through the rest of your college career and into your career as an engineer, which means that the best day to learn statics is today. We're currently looking at rigid body equilibrium in our analysis phase, so we're going to continue to use force vectors. We're continuing to look at force systems and centroids, and we're even doing our rigid body equilibrium, but now we're going to take it a step further. In many ways, there's no new content for us to talk about now. It's just new ways of applying that rigid body equilibrium that makes up the heart and soul of statics. And so with that, I want to talk about frames and machines. And so I've got an example here of a mail bag hook for trains. So they'd hold the mail and it would catch on the train without the train having to stop. And I hope what you can notice is that it looks like that hook has, especially that top horizontal bar, actually has three different members, and those things are pinned together. That's kind of interesting. Another example might be for my mechanical engineers, maybe someday you want to grow up to design a new ironing board. And if we look at that ironing board, we notice that the top plane looks like a member. And then underneath, it's got some connections there to two of those cross members. Those cross members meet at a pin. And this particular ironing board even has a little shelf there that also looks like it has some pins and rollers going on there. So those are things we've talked about before. Or for my construction engineering students, we have a backhoe here, and this is made up of several different members. We see the two big main members, but I hope you also notice those hydraulic pistons that are acting along the way, and those are also pin connected. So it turns out when we're talking about frames and machines, that in order for us to define those things, a frame and a machine, these are basically the same thing, just depending on what they're using. So frames would typically be used to hold things in place. Statics, yes. And machines would be the same design, but intended to move things. So dynamics, that's next semester. In both cases, frames and machines are made up of multiple members that are pin connected. In order for us to have a proper frame, we're going to treat each different element as it were pin connected. Pin connected. And furthermore, in order for us to have a statically determinate frame, a frame that we can analyze using statics and the tools that we'll talk about today, typically we only have two members. Remember, MBRS, it's our abbreviation for members, at each pin. So you'll notice, like on the backhoe in our slide here, that the hydraulics come in, and you can see here on the picture where the hydraulics join and meet at a pin. So we have one member and another member joined at a pin. Same thing here. Even with the ironing board, we have the same idea, two members and a pin. And that's going to be very important. Later we'll talk about trusses, that because they have different assumptions, we can analyze them even though there's more than one member joining at a pin. But for the case of frames and machines, we're talking about two members at each pin. Furthermore, these members can be loaded anywhere. And an implication of that is that these are going to be multi-force members, meaning that there can be loads not only at the pins, but also in between the pins in different places. So again, if we look at our nice little backhoe there, we can see that there's a pin that would generate a load on this arm. There's a pin here where it joins. There's another pin where the hydraulics, and then a pin where the bucket actually attaches. And so all of those things working together mean that we have multiple loading points on this particular frame. Similarly, for the ironing board picture, we see that there's a load there. There's the load associated with the basket. We might model that as a distributed load. There's the load from the iron, another pin load there. And so it's loaded at a lot of different places, which just is one of the assumptions that goes into our frame analysis. Now, when we do a frame analysis like this, what we'll end up doing is we'll end up pulling the pins and breaking that apart. So when we think about a procedure for analyzing this type of structure, for each member, we're going to draw a free body diagram, FBD, free body diagram, for each and every member. So the idea is that kind of our phrase will be to pull the pins. And what happens when you pull the pin? Well, that whole structure is going to come apart. And so again, if we look at our ironing board, or maybe let's go back and even look at this this guy over here, the male arm. We might have, see, it's got, looks like some pieces like that, yeah, with some weight, some sort of object hanging out here, something like that. So if each one of these points, blow that back up, is a pin, we're going to pull the pin. So we're going to unhook each pin. Now, in this case, this was a continuous member. That's also a continuous member. So when we pull the pins, we're going to get different things going on. So first off, we pull the pins, and then that will expose the joint forces. So currently, if we were to solve for the external reactions on this frame, here we can even put in a connection to the bottom that's a fixed connection. So it's going to have two forces and a moment acting on it. That when we expose the internal joint forces, that's going to be represented by two perpendicular forces with no moment. So this is exactly the same as it was when we were talking about pin connections in those external supports, where we had a pin, we'd have a force in the Y and a force in the X, but no moment because it's free to rotate. So in the case of frames, when we pull these pins, we're going to have to replace those pins with these external forces. Now, Newton's third law tells us that for every action, there's an equal and opposite reaction. So for any force acting on, say, this member, there's going to be an equal and opposite force acting on the other member. And so that means that we're going to have equal and opposite joint forces on each member. So equal and opposite joint forces on each member. So if we were to take our frame that we've sketched over here and break it into its three components, we'd have a component that looks something like this, and we'd have a component that looks something like this, and we'd have a component that looks something like this. And in each case, we're going to have those equal and opposite forces. So where I pulled the pin here, I'm going to have a force that goes like that, right? So I got my two forces at that pin location. Let me draw that a little bigger, a little easier for everybody to see. A little bit more space. Okay, so pin and pin, pin, pin. So over here at this joint, I'll have a force like so, which means that this joint, so remember these pins are the same pin, we pulled them, right? It's right up here. If I pulled it, I've got two different locations. I'm going to have the same forces equal in magnitude, but opposite in direction. So this one's drawn up, so I'll draw this one down. This one's drawn to the right, so I'll draw this one to the left. This is the first time that we've ever encountered a situation where we would really want to go through and abandon our sign convention that we're always going to draw in the positive direction. Over here, I certainly did, but here I'm being driven by that equal and opposite. So if I was to label these, let's go through and label some locations. Maybe we say A, B, C, D, E, right? I might call this down here, since this is joint D, FDX and FDY. Over here, I'd have the same magnitude, FDX and FDY. And this is why it was so important that when we draw our arrows, we use those to indicate direction, not a plus or minus, because that can get confusing when we're doing that. So likewise, I can go through the rest of the structure and do a similar sort of thing. I can have FBX and FBY. Now, if I do that, right, the other joint B is over here on this member. So I got to draw them equal and opposite. So FBX was to the right there, so it's got to be to the left over here. FBX. Oop, I did that wrong. It's not FBY up, it's got to be down. So FBY. So again, equal and opposite. So at this joint over here, I might have FCX and FCY. And then here, equal and opposite. So this is going to be FCY and FCX. What other forces do I need to put on here? Well, I've got my load out here, so I would probably have a force at E that's driving the load. And then I had a fixed connection down here. And so a fixed connection in 2D is going to give me a vertical force, FAY, FAX. And because it's also fixed, it needs a moment. M about point A as my moment reaction. And so now I have, let's see, it's gotten a little cluttered, but the idea here is that I have 3 separate free body diagrams, right? Something like that, 3 separate free body diagrams. And each free body diagram is going to have its own equations of equilibrium. So over here, once I've done my free body diagram for each case, I can write the equations of equilibrium. Now, we won't do that for this problem right here, but I will point out that we'd have up to 9 equations, right? So 1 here, that's 3, 3, and 3. In addition, we could do 1 for the big structure, but that's a little extra, right? So 9 equations. How many unknowns have we identified here? So we looked at just the joint forces. We have 1, 2, and then they're the same over here. So nothing new there. So 1, 2, 3, 4 at D, 5, 6 at C. We're doing pretty well. Another 3, that puts us at 9, assuming FE is a known. I got 9 unknowns and 9 equations. May not be the most fun to solve, but I certainly can. So we'll write our equations of equilibrium, and then we'll solve for our unknowns. So the idea with frames and machines, just to review, is that they're pin connected. In order for us to analyze them using this method, we'd only have 2 members at each pin. Furthermore, they can be loaded anywhere, so we're not restricted. We can use multi-force members. Our procedure is going to be to break them down so that we do a free body diagram by pulling the pin, exposing the internal joint forces, meaning that we're going to have 2 perpendicular forces at each joint, and then they're going to be equal and opposite on each member at each joint, just like we did over there. We'll write our equations of equilibrium for each free body diagram, 3 equations each for this case, and then we'll be able to solve for our unknowns. So I hope that helps, and I look forward to working a problem together with you in class.